All right, I'm talking about something with p-adic. So as always, my talk starts with P. P is a prime number throughout the talk. F is either a finite extension of QP or the Laurent series of a finite field. So actually, did you turn on the mic in the room as well? If you can't hear me, let me know, or if you can't see, or if I need to raise the blackboard, repeat questions, just shout at me. So F is a non-Archimedean local field. Inside F, I pick a ring of integer, and the residue field is FQ, just in case we need that. And then the main player for today, for this talk, is denoted by G. G is a connected reductive group over the local field F. So GLN, SLN, exceptional groups, whatever you like. The only restriction I want to make is I assume that the group G splits over a tame extension. Splits over a tame ramified extension of the field F. So GLN of a division algebra is perfectly fine because it becomes GLN over a tame extension. I guess most groups you naturally encounter are fine. That's just to make my life easier because a lot of results only work in that setting. All right, what is the goal? The big goal is that mathematicians have been working on for some time is the following. We want to understand, and by understand, I mean rather explicitly understand the category of smooth representations of our p-adic group. Want to understand the category of smooth representations, and let me put complex here. So I look at representations with complex coefficients, smooth complex representations of G of F. G of F is what I often call the p-adic group, even though it might be also over the Laurent series. Smooth always means the stabilizer of every vector contains an open. So this is a nice category, and that's what we try to understand. How do we do this? Well, people who have seen me giving talks before know that there are certain building blocks. And today I want to go beyond these building blocks. The building blocks, they are called supercuspidal representations. There are a lot of people in this audience who are very familiar with them, others who might be less happy with them, or at least if we work with complex coefficients and groups other than GL2 or so. And these are the building blocks, meaning that if you take any irreducible representation, and when I say irreducible representation, I always mean smooth. Representations from now on are smooth. If you take such an irreducible smooth representation of our group G of F, then this representation embeds into some parabolic induction from a parabolic subgroup to the whole group itself of a representation sigma, where sigma is a supercuspidal representation of the Levi subgroup of P. So P is M times N. P might be equal to G. Oh, thank you. Thank you. Thank you. K is F. No, K is not F, but this should be F. Thanks. So that means every representation occurs in the parabolic induction of some supercuspidal representations, and the supercuspidal representation are those that do not occur in a proper parabolic induction. So they occur only if you take P equals G here. So these are the building blocks. These are the ones that are difficult to construct. So we knew that everything occurs in parabolic induction for more than 50 years by now, I think. And in the last 50 years, people actually tried to construct these supercuspidal representations. So let's give it a bit more. So that's the first problem that I want to talk about. The first out of two problems is construct all the supercuspidal representations of our p-adic group. Supercuspidal will be abbreviated by SC from now on most of the time. And so here is the spoiler. The vague answer is that we can do this almost all the time. Can do it almost all the time. And I will make this more precise in the first part of the talk when we can do it. And this has been the work of a lot of mathematicians. People have been working on this the last 50 years. So that's problem one. Problem one is to find these supercuspidal representations, and doing it explicitly has a lot of advantages. I mean, we knew already they are the building blocks, but if we are able to write them down explicitly, we can actually study them much more easily when we want to study all kinds of questions in the representation theory, like what happens when you restrict the representation to a subgroup? What happens when you put representations into the Howard correspondence? How do you calculate the characters of these? So the Chandra characters, the analog of characters of representation of finite groups. For all these questions, it's really helpful to be able to write them down explicitly. Or if you want to write down an explicit local Langlands correspondence, you want to write them down explicitly. Or even if you want to study automorphic form, the global Langlands correspondence, for all these questions, it's actually helpful to have explicit constructions. So that's the first step. But I said we want to understand the category of all representations, so we can't stop here. So the next step is that we use the Bernstein decomposition that came up already in David Holmes' talk yesterday. But let me recall it. I don't assume that everyone necessarily has been there or memorizes everything that happens in previous talks. So let me denote the category of smooth representations by this curly R. So then Bernstein told us already many years ago, 40 or so years ago, that the category decomposes into a direct product indexed by Levi subgroups, like this M up there, and supercuspidal representation. So the product runs over pairs M sigma up to some equivalence, and each block corresponds then to the representations whose irreducible subquotients are contained. We know that all the irreducible representations are contained in some parabolic induction, and now we group all those together that are contained in a specific parabolic induction from a parabolic, say P prime of sigma prime, where P prime is equal to M prime times M prime, and this M prime sigma prime is a pair that's in the equivalence class of this M sigma. So we take an M sigma, take its equivalence class. Equivalence class means if we have a pair M sigma, this is equivalent to the following. Obviously, you're allowed to conjugate the Levi subgroup by some element G in the group. And then you have to conjugate the representation accordingly, because if you induce something conjugate to G, you get equivalent representations. And you're also allowed to twist by some unramified characters. And then we build the Bernstein block by just taking a Levi and a supercuspidal representation. So this sigma is supercuspidal, and inducing all the way up, doing this for all in the equivalence class, and then take everything that we can build out of that. And that's a block, and the category decomposes into these blocks. So that's something that has been known for a long time as well. So that means if we want to understand the whole category, the second problem is that we want to understand, let's call it 2, understand how these Bernstein blocks look like. So first problem is understand how these index set looks like, M and sigma. The sigma is a supercuspidal representation. Second problem is, once we know that, how do we describe the Bernstein blocks? Once we know that, we know everything. Let me just give you an example so that you actually, our Bernstein blocks look at first very abstract. So let me give you an example. The case SA2. Of course, the example SA2 is comparably easy, but it's therefore I'm using it to be able to write something down. So there are two interesting cases that I would like to mention. The first one is that we can just take M equals to G. So that means we look at the block where M is equal to G, and then sigma is just a supercuspidal representation of G. So that's basically what we understand thanks to problem 1. And well, this is just the objects in this category are just the representation plus itself, the representation plus itself, and so on. So this everything splits here. This is projective, so it's rather easy. In general, for semi-simple groups, that's how the supercuspidal blocks look like. When you have center, it's getting a bit more difficult. That's one extreme, and the other extreme is the case that M is just the maximal split torus. And in that case, if we, for example, look at the block corresponding to this torus and the trivial character on it, for torus, everything is supercuspidal because it doesn't have parabolic subgroups. So in particular, we can look at the trivial character. Then this is much more complicated. It contains, in particular, the trivial representation. That it's more complicated. It's called the principal block, I think. And that's one of the questions for this talk. We want to understand that block. Some of you might already know the answer to that question, since this is a rather easy one. But in the end, we want to understand all the blocks. So that's what we want to do. Let me give you also the spoiler. So close your ears if you don't want to hear it. The vague answer to problem 2 is the following. It's, let me call it an expected theorem, because it's expected because it's work in progress. We are writing, we hope we can prove it, but you know, when you, sure. Far enough? Or excellent. So it's expected because, well, we are in the process of writing things up, and we all know when we write things up, we might encounter more abstractions, which I don't hope. It's a joint work in progress. The paper will be with Jeff Adler and like Manish, Mishra, and Kazuma, Ohara, who might be somewhere in the audience. Here he is, so second work. And that's work in progress. And I said vague answer. So what is the vague answer? The vague answer is that this Bernstein block, an arbitrary Bernstein block, at least if we assume that P doesn't divide the order of the Weyl group, is, well, that's why it's all vague, is isomorphic to something, well, that doesn't help you much yet, but I'll say a few things about this, which is the same where I just put a 0 everywhere. And what is this? So sigma 0 is a depth 0 representation, and I will say more about this throughout my talk. But so what you should actually take away from it for now is that this Bernstein block is rather well, let me put it in quotation mark, because what is well understood in math, rather well understood. So this has been studied already by Morris in '93. And since then, we rather understand this rather well, up to a lot of small details that I'm addressing later in the talk. But so the rough idea is we knew already how the depth 0 blocks look like. And now we know that all blocks are equivalent to depth 0 blocks. Why is this an interesting result? Well, first of all, because they are much better understood and we can understand these blocks now, but also because a lot of questions are much easier for depth 0 representations. Depth 0 representation, they correspond basically to representations of finite groups of Lie type. We've seen that in Charlotte Chan's talk. She started with the depth 0 one, and then that was these G0, and then went to the higher ones, GR. And a lot of questions are much easier to study for depth 0 representations than for arbitrary representations. And so now it allows us to reduce things back to depth zero representations for many questions in representation theory, but also beyond. For example, I expect this will help us to maybe write down a more general local Langlands correspondence and explicit Langlands correspondence, or also a categorical local Langlands correspondence. So far, the categorical local Langlands correspondence, I expect might in the near future be known for depth zero representations, and then we can use this equivalence to actually get a local Langlands, a categorical local Langlands correspondence in full generality. That's the hope and one potential application of all of that. I always assume the groups will over time extension, and to have that for all blocks, I assume that P doesn't divide the order of the Y group. I'll make this more precise later, but that's, yeah, I mean, that statement is now very precise. I just allowed myself to skip the detail. G0, excellent question. I haven't told you yet either. G0 is a subgroup of G. It's a twisted Levy subgroup, which means it becomes isomorphic to a Levy subgroup over some time extension. So for example, for SL2, this G0 could be either SL2 itself, or it could be the split diagonal torus, or it could be an anisotropic torus. So something like matrices of the form A, B, B, uniformizer, something of that form, for example. If sigma is always supercuspidal. Sigma is always supercuspidal. Okay, so sigma is supercuspidal. These are no longer, these are blocks that are not necessarily supercuspidal, and the supercuspidal support is sigma. So these are the representation arising from parabolic induction of sigma. All right, more questions? If the let's ask me that at the end. I don't think that helps right now. G0 is not a fixed group that depends on what representations you start with here. Yeah. Yeah. Is there a choice involved? Yes, but let me maybe answer that towards the end when I tell you how this equivalence comes about. Oh, sorry, that's too high up now for some. All right. So we have problem one, problem two. Let's dive into it. Problem one is the construction of supercuspidal representations. And let me also say, and of types, without having told you yet what types are. I'm telling you afterwards the definition of types. It doesn't really matter for now. I just don't want to have to write the same twice. All right. So what do we know? When can we construct these supercuspidal representations? Construction of supercuspidal representations is known for groups like, well, people start to work with GL2 and then GLN. So for GLN, we know everything. That started more than 50 years ago, I think, with work of Howe and Moy, and was then finished around 30 years ago by Bushnell and Kutzko. So that we understand rather well. SLN, we also understand thanks to Bushnell and Kutzko, and types then thanks added on by Goldberg and Roche. Classical groups, if P is not equal to 2, we also understand thanks to the work of Sean Stevens, and then types, I think, Miyuchi and Stevens together. The idea for classical groups, these are fixed points of an involution in GLN. And the idea is just to use the approach for GLN and make everything invariant and let the involution that defines the classical group. It's not as easy as I just said it, but that's the main idea. We also know it for inner forms of GLN, thanks to work of Secher and Stevens. So that's just GLN over division algebra. Again, it's the same techniques as GLN. But today I want to talk about the setting for all groups together. So what do we know for general G? So for general groups G, it took mathematicians much longer to somehow get somewhere because a new language had to be developed. Rather than for GLN, you have matrices, so you can look at the vector spaces corresponding to that and let this change in there. For general groups, we had to wait for Bure and Tietz to develop Bure and Tietz theory, and then Moy and Prasad to develop a filtration of those. So let's see if I draw a picture. Let's see how I do this. Let me draw. Some people might have seen that already. I draw a picture, oops, where the arrow goes down. That's the depth. So here's 0, and then down there is the depth of the representation. What is the depth? I said the representation is smooth if the stabilizer of every vector contains an open subgroup. And now what Moy and Prasad did, so let me write down the names, Moy and Prasad. That was in 1994, 96, Moy and Prasad. They defined the notion of a depth by defining a filtration by compact open subgroups that are getting smaller and smaller and smaller. And the depth is then the question, how far do I have to go down in the filtration until I get fixed vectors? That's the depth. And then the depth 0 representations are up here. Let me draw in this direction the prime number p, because some results depend on the prime number p. And so Moy and Prasad, they studied these depth 0 representations up here. So that's what Moy and Prasad did. And I should also say Morris did the same roughly around the same time. Morris did this in 93 and 99 using a bit different approach, using an approach via Hecke algebras. And they tell you how to obtain all the depth 0 representations, modular understanding representation of finite groups of Lie types, which of course is very difficult in its own. So that's Deligne-Lustig theory, and Lustig has done a lot of work on that, and it's still not fully understood. So that's the depth 0. And these are the representations that we want to relate everything back to eventually. So I was asked, or let me just answer the question by thereby stating, so depth 0 means we take a point in the Bure-Tietz building that has a parahoric subgroup, doesn't have to be a vertex. For general depth 0 representation, for supercuspidal, it has to be a vertex. For general depth 0, it doesn't have to be a vertex. And then we look at the pro-p unipotent radical of that, which is the 0 plus p's. And if it has fixed vector under that, then it's a depth 0 representation. Maybe let me just give you one example here. So you already see an example of a supercuspidal representation. Let's say G is SA2. Then one example would be that we take SA2 over our field F, over our field O. That would be the stabilizer of a vertex. We project down onto SA2 over a finite field. So that's modding out by the pro-unipotent radical. And then we have now a finite group of Lie type. So we can compose this now with a representation. Let me call this rho, so a map to the space of automorphism of some finite vector space where this is a cuspidal representation. So that's now a representation of a compact subgroup. And how do we get a supercuspidal representation out of that? We just take the compact induction from this group SL2O to the whole group of this representation rho. So these are just all the functions from the group to the vector space such that the function is compactly supported, and now I'm really tight on space, such that f of, I hope this is still readable, kg is equal to rho of k times f of g. And now I can't fit in anymore what k and g is. So k is an element in this SL2O, and g is any element in our group. So that's how we can obtain a depth zero supercuspidal representation by taking something over the ring of integer, essentially modding out the pro-p unipotent radical, and then taking a cuspidal representation. So cuspidal, same as for supercuspidal, not a subquotient of a parabolic induction, now over the finite field. And then we take the compact induction. And that's how we obtain all the depth zero supercuspidal representations. And indeed, for the depth zero supercuspidal representations, we have to start with a vertex or minimal point in the building. Oh, sorry, that was not a question. Excellent. So that's step zero. And so that's what we want to relate everything back to eventually. Well, of course, if we want to relate everything back to it, we want to understand how the higher depth pieces look like. And so that the first big attempt in that direction happened in 1998. Is this readable, blue? Okay, that's not readable. Is this readable? I get. Okay, why 1998, 2001, that's there was a PhD thesis of Jeffrey Adler, and then it was vastly generalized by JKU. And let me just circle this in green. So that's the green part. What did they do? Well, they constructed a lot of representation. So a lot of things is what they constructed down here. I don't know if this is, if you can see that, but it's just a lot of representations there. And that's what they did. Oh, I should also say, maybe add a few more names. If we talk about types, I should add the name Kim as well. They did this in 2017. They observed that use construction can be relaxed to obtain types. The date is so late just because I think they didn't publish it earlier for no good reason. Maybe I'll also put my name there to fixing a few things. And so that means now we have a lot of representations out there, a lot of supercuspidal representations. And the question is this everything? If we want to relate everything back to depth zero, we want to first of all find everything. And so that's what Julie Kim then showed in 2007. Is that readable? Okay, wow, I found the color. And Julie Kim showed that actually, if we are in this region here, where the prime P is very large, very, very large, then we get all the representations coming from JKU's construction. So Julie Kim showed that U's construction is exhaustive if P is very, 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 very large, and if the characteristic of the local field is equal to zero. So if we are in the case that the characteristic is zero, so finite extension of QP, then we get everything from JKU's construction. And we also get all the types from Kim-U's construction. Now I have to figure out how to use the blackboards the best. Let me just switch them. So that's problem one. We try to construct all supercuspidal representations. And I said the vague answers, we can do this. So we are getting there right now. So we are almost there. It reminds me of doing sports with kids. We are almost there. Keep fighting. 30 more seconds. And there we are. What color? Orange. So we have a lot of representations that you might not be able to see because it's green on green. So just imagine they are there. And now the result is that if P is just large, not super large, just large, we get exhaustion, we get all supercuspidal representations coming from use construction, and we don't have to assume that the characteristic is equal to 0. So that happened in 2021, I think, is when it got published. Thanks to all the referees who worked during the pandemic, which says that, oh, I guess I should attribute it also to myself. Use construction is exhaustive exhaust all the supercuspidal representation if P doesn't divide the order of the Y group of the group. So for example, for GLN, that would mean P is greater than N. For exceptional groups, in the worst case, you exclude 2, 3, 5, 7, that's it. And the same for types. So also for Kim use construction of types as well. Construction is also exhaustive under the same assumption. And I still haven't told you what types are. I'm aware of that. All right. And now I ran out of colors. I think I have yellow here. So there's still a bit missing. But I also said the vague answers, we can almost do it. So there are more things missing. And we know that there's more here. There are more dots here. So some dots here have been already constructed by combining work of Reader and you together with myself and Romano and myself and Romano. And what we're currently working on is to find more representations here. So that's, let's say, future. So let me be optimistic, pessimistic, whatever, and let's claim in 2024 there will be a paper by myself together with my postdoc in which we construct some new supercuspidal representations there. So that's where we are heading to, trying to find the remaining supercuspidal representations. Since that's so that paper that's not yet existing will construct, no pressure at all, supercuspidal representations of positive depth. And then if you combine it with that paper, which hopefully exists in a few months already, you will get the result that the category, that you get that higher, deeper Bernstein blocks are equivalent to depth 0 Bernstein blocks. And so we are writing this result in such a general setting that we hope it will apply to that paper as well once that paper is written. Yeah, this is known for GLN. For GLN, I'm not telling you anything new today. All right, let's see. So that's the supercuspidal representation story. Now I can get for that. Now I want to move, that was the answer to problem 1, up to question mark and reference to the future. The answer to problem 2 is now what I would like to go into next. So for that, I need to introduce types. So you already know that types exist. They exist as long as P doesn't divide the order of the Y group. But what are they? So, oops, here's the definition. A pair K, comma, rho. Oh, maybe before I write down the type, let me make one more comment. Let me make this comment on the side. Remark, all these supercuspidal representations, all these supercuspidal representations are constructed via compact induction. So you take a compact induction from some compact mod center open subgroup to the whole group itself of some representation rho. So for example, I've written down for you an example there, so I will not write out again what compact induction is. That's compact induction. You have these functions. So roughly you have functions on the space G mod K, which is an infinite dimensional vector space, and all these supercuspidal representations are of that form. So it already shows you that compact open subgroups here mod center soon for real, together with representations, carry a lot of information about the representations themselves. So for supercuspidal representation, they carry all the information. And type theory is now the idea to obtain all the information about non-supercuspidal representations as well by studying compact open subgroups together with representations. So a pair consisting of K being a compact open subgroup of our group G of F, not K, G of F, and rho being an irreducible smooth representation of K. So that's just a finite dimensional representation factors through some finite quotient, which are these finite quotients we've seen in Charlotte Chan's talk. Such a pair is called a type. And more precisely, it's called an M sigma type. Oh, could someone maybe close the windows there? It's getting too loud. An M sigma type. Now, what is M sigma? M sigma is always a Levi subgroup and a supercuspidal representation. So it's an M sigma type for this Bernstein block. If the following are equivalent, if the following two are equivalent, before I write this, let me say for what? If for all pi irreducible smooth representations of G of K, G of F, the following are equivalent. And the first one is that this representation actually lies inside the Bernstein block. Did I say just R? Yeah, I just wrote R over there. Inside this Bernstein block corresponding to M and sigma. That was a mistake. That's the one condition. And the second condition is that we want to detect which Bernstein block it lies in via this compact open subgroup. So the second condition is that if we take the representation, pi and restrict it to this compact open subgroup, then it becomes semi-simple, and then we want it to contain the representation rho. So that means we can detect if the representation pi lies in our chosen Bernstein block by restricting the representation to K and checking if it contains rho or not. That's a type. All right. Oh, here's a nice example already. So let me keep that example. How do I keep that example? G equals SA2. How do types look like? A type in the case A, well, that in the case A, it would just be the super, okay, sorry, that requires. In the case A, this is the supercuspidal representation. So sigma, in that case, is the compact induction. Say we take, let's take the example up there. Let's say sigma is the compact induction from SL2 of O to G of F of this representation rho up there. Then in that case, the pair SL2O together with this representation rho, this cuspidal representation, is an type for this Bernstein block. So is an G sigma type. So in the case of supercuspidal representations, it's essentially just the datum that we use to construct them. In the second example, we looked at this principal block. In the second example, a type for this principal block would be taking the Ihara subgroup together with a trivial representation. So we call Ihara subgroup inside SL2O, just corresponds to the matrices that are upper triangular when you mod out by the pro-unipotent radical. And so if you take the Ohara together as a trivial representation, this is a type for this principal block, is an torus together with trivial representation type. So these are two examples of types. But why am I writing down these types? Well, one reason is already, you see, they tell you which Bernstein block you're in, but they have even more power. Here comes the power. Factor of Bushnell and Kutzko from, I think, 1998 says that they are so powerful that they actually tell you what these what the Bernstein block is based on the type. So let's say K rho is an M sigma type. Then they show the following. They show that the Bernstein block corresponding to M and sigma is equivalent to the category of right unital modules over a certain Hecke algebra attached to that type. So what is this curly H? Curly H is defined to be all those functions from G. Now, if you look, that's the compact induction up there. It's functions from G to the vector space. Now we take functions from G to the space of endomorphisms of that space, just C linear endomorphisms, such that as above, F is compactly supported. But now we have this transformation, this relation on both sides. Now we have that F of K, G, K prime is equal to rho of K, F of G, rho of K prime for, well, as you can imagine, K, K prime inside capital K, our compact open subgroup, and rho is rho, and G is inside G. So you see there's a big similarity. And so this forms an algebra using convolution. I'm not writing down convolution for you now. Another way of interpreting this is what we have seen yesterday, is that this can be also thought of the endomorphisms of the compact induction from K to the whole group of rho. So if we work with a supercuspidal representation and our group doesn't have any interesting center, say doesn't have any center, then this compact induction is might provide us with supercuspidal representations, then it's irreducible, the endomorphism space is trivial. But if we are not in a supercuspidal block, then it's far from irreducible, and the space of endomorphism actually tells us how to understand the Bernstein block. And here the algebra is just obtained by composing endomorphisms. All right, so that's what types are. Oh, too far. All right. To keep the balance between me not covering it and you seeing everything when it's not, so that's not too high. Okay. Is the K rho uniquely determined by the M sigma? Excellent question and research problem. It's so you could first of all ask this for supercuspidal representations as a first step. And even there, it's not known in full generality yet. I think we know it for GLN if you define an equivalence appropriately, thanks to Vitas Pascunas, I believe. Potentially, he looks a bit confused. This was his thesis, his PhD thesis is what he is telling us. We know some special cases, but it's not known in full generality yet. Oh, so there is apparently a PhD thesis currently in the making, or where they show it, it's not unique for GLN of a division algebra. Oh, that's great. I'd like to learn more about that. So that's the answer. I love this audience. Thanks. So here are types. Where are we going? We have the Hecke algebra. So we now see that the Bernstein block is equivalent to modules over Hecke algebra. So, well, we need to understand the Hecke algebra. What is the Hecke algebra? That's the big question. Let me maybe first of all give you an example. For the first example of supercuspidal one, the Hecke algebra is just C. It's rather boring. The second example up there. So if we have the Hecke algebra attached to the Eva-Hori and the trivial representation, you can just read off from how I define it. These are just the compactly supported functions on the double cosets of G mod out by the Eva-Hori on both sides, because that's the condition we have put on there. The question is just, can we understand this more explicitly? For the Eva-Hori, some people say, oh, of course, that's trivial. That's true. Well, it's non-trivial, but it's doable. Let me just write out this example so you those who haven't seen it before, you see how that looks like. So in this case, this is as a vector space. It's just, well, it's the algebra by the complex numbers indexed by some generators T sub W, where W is an element of capital W. Well, that doesn't help you anything until I tell you what this is. This is the affine Mile group. It's generated by two generators S0, S1 with the relation that they squared equals the identity. So this group is just the reflection subgroup you obtain by taking 2 points and taking the reflection across one, the reflection across the other, and then take the group generated by that. This is so far only true as a vector space. I have to tell you what the relations are. And the relations are of the form T sub Si times T sub W is equal to, there are two options. The easy option is that it's just TSIW if it's length additive. So if the length of Si times length of W is greater than the length of W. And otherwise, there's this relation that people might have seen before, that this is equal to Q times T of W plus Q minus 1, if I get it correctly. Oh, no, sorry, SIW and W otherwise. And of course, you have to do the same relations with TW, TSI. It doesn't really matter the details of that. It's more like if you're used to affine Mile groups, it's the same thing here. All right, so that's how these objects look like in the special case, and we want to understand them in general. And so in 1993, Morris actually gave an explicit, rather explicit description of the Hecke algebra, or rather, to make it precise, I should say, no, I can say of the Hecke algebra, okay, though corresponding to a union of, and union of sounds horrible, so let's ignore that. Let me find some. Just ignore that, and well, you in our paper we'll also tell you why you can ignore that. Corresponding to depth, or corresponding to a depth 0 type. Or maybe I should say a depth 0 Bernstein block. Bernstein block. So by this, I mean corresponding to a Bernstein block with M sigma, where sigma is supercuspidal and depth 0. And so by explicit, I mean that he wrote down generators and relations And so this Hecke algebra is just the semi-direct product of an affine Hecke algebra. So affine Hecke algebra is like this thing, just for general affine Weyl groups, with a twisted group algebra. So that's what it is. And Morris wrote down already in 93 an explicit description of such things. So there we are in 93. So luckily it's, oh my God, it's already 2023. So that means we are 30 years later. So I hope I can, well, I still have a few minutes left. That's great. So I can tell you that this is not the end of the story. So here is the dream that people have been dreaming for a long time. People thought they had counterexamples to it. People thought it's obviously true, but they didn't know how to prove it. What is the dream? The dream is that every Hecke algebra looks like that. Like here we have the depth zero Hecke algebra. So the dream is everything looks like that. Let me make this more precise. So let K rho be a Kim-U type. For some Bernstein block M sigma. So it's an M sigma type. That's maybe how I should have written it. So let K rho be an M sigma type, but of the form constructed by Kim and Yu, which is the one that I've just erased here. So almost everything, if P doesn't divide the order of the Y group, every Bernstein block has such a type. So that's not a big restriction. So let K rho be a Kim-U type. So then the hope is, the dream is there exists a G0 inside G, some twisted Levy subgroup, and a K0 rho 0, a type. And let me put it in here, an M0 sigma 0 type, where M0 is a Levy subgroup of G0, and sigma 0 is a depth 0 supercuspidal representation. So the hope is, starting with an arbitrary type, we can find a depth 0 type such that the Hecke algebra, well, now I wrote the group as well just to clarify, because we have two different groups, is isomorphic to the depth 0 Hecke algebra. And this is the depth 0 Hecke algebra that is, let me say, just known by Morris. So that's well, okay, there's the Christian complaint, I don't know what, that there's no dream if there's no Kim-U type. Well, there is actually the dream that there exists a type for all Bernstein blocks, and then the statement will hold for all Bernstein blocks as well. Yeah. So second dream is there exist types for all Bernstein blocks, but I'm not sure they should be called Kim-U types. Yeah, so our results is in full generality also addressing potential future types. But now I'm working with what's there for this talk. See, I have 5 minutes left. Excellent. So that's the dream. And well, we can all dream, but let's see, when is the dream true? Dream is true. Or before I say the dream is, when the dream is true, let me just make one remark that as a corollary, of course, as a corollary, you obtain that an arbitrary Bernstein block this corresponding M sigma Bernstein block is isomorphic to the Bernstein block for the depth zero representation. So that's the vague result I started with. Now it's actually made precise as a dream once we prove the dream. So the dream is true for GLN. Someone already said that, yes, for GLN, it's true and known for quite some time, thanks to the work of Bushnell and Kurzke that introduced all these type theory and wrote down all the types for GLN. For classical, let's see, for SLN, thanks to Goldbeck and Roche, I believe you can deduce it as well. For classical groups, I haven't seen it yet in the literature explicitly, but Heyermann has a lot of work on Hecke algebra, also based on work of Langlands, so maybe you can deduce it there as well. But beyond that, it's not so known. And what are the results for general groups G? So for general groups G, the case that M is equal to T is split maximal torus inside G. So in particular, G is also split. That has been done by Roche in, I think, 1998 or 1993. My memory is not the greatest. So sometimes in the 90s, before I had my PhD. And then not much has happened for a while. And recently, the case that M is equal to G was solved by Kazuma Ohara in 2021. And the special case of M equals G when the Hecke algebras are abelian has been solved by Mishra a few years earlier. And that was actually it until recently. And so well, I already gave you the spoiler, the expected theorem in a joint paper with Jeffrey Adler, Manish, Mishra, and Kazuma Ohara, who is sitting in the second row here, in progress, is that the dream is always here. So that's the result. Oh, and I still have a minute. Wow. So that's true. Well, okay. That's the expected result, which we are currently working on proving. Since it's a work in progress, let me maybe, and it's a long proof anyways, I won't say too much about the details of the proof. I just wanted to make one remark. Maybe I can write this even down, or maybe two remarks. First remark is, if you sit down and try to prove it, you see rather easily that there's a support preserving isomorphism. And the tricky part is to show that it's an algebra isomorphism. And I might give another talk about this at some point when we've written up the details. That's much more complicated, but just one remark, and since I was told 2 minutes, not just one, I can even write the remark down, is that the proof relies on extending the quadratic twist of JKU's construction, or of the Kim-U construction, that was introduced by myself and joint work with Tasho Kaletha and Lawrence Spice. So those who have seen me giving talks 1 or 2 years ago about our quadratic twist of the construction, I already mentioned potential applications to Hecke algebra isomorphisms, and that's the big application. So it's really important that we have this twist in. I could talk about this a whole another hour, but I just wanted to put this out here. And we can't just work with the twist, we have to extend it. So that's just one of zillions of technicalities that go into the proof. I think now my 2 minutes are up. Thank you very much.